Greetings from SCDS KCT. It's a pleasure for me to welcome you all to Cosmorena 2020. Today is the first day of the webinar on Rover by SEDS-VIT. A small information about the certificates. Feedback form will be posted in the chat box at the end of the session. Certificates will be provided only for the participants who fill the form and attend both the days of the webinar. I again welcome you all to Cosmorena 2020. It's too hard to learn driving and getting a license on a blue planet.
basically, you can see the two rods which are moving from the wheels to the chassis. So these are the wishbones that make up the bigger part of the suspension system. Now, these bones are hinged to the chassis with the connectors on the top, which make sure that the movement is restricted to the suspension itself and the chassis stays flat, parallel to the ground. Third, but sometimes what happens is the shock that is imparted from the sudden movement is so big that we can't uh, presume the chassis to stay parallel to the ground. So what happens in that case is that the dampers that we are attaching to the mechanism, they are there to absorb the extra shock that is imparted from the movements and make sure that the chassis stays parallel and the components which we want are there when we need it. So, yeah. Next up, we have a short video about the functioning of the rover. It's a bit of a poor light, sorry about that. But yeah. Yeah. So this is basically how we want it to function, and it's doing its job. So when it's moving over the rocks, the chassis is comparatively still parallel to the ground, and all the components are in their place, and they are not going or moving from place to place, and it functions when it's over that obstacle. So yeah, now we have got the third component with us, uh, which is the wheels. Yeah. So if we talk about the wheels in general, everyone knows what wheels are, like the round shapes that help us in the travel. And now, like, why do we use wheels basically? So I don't think like there is any explanation that I can give for the why wheels. Everyone knows why we use wheels and what are wheels, but I'll try to explain it in a different way. So wheels are important because that's where we start the design philosophy of the rover. We start the designing process of a rover starting from the wheels. We first decide what kind of wheel we are going to use, what is the diameter, what is the width of the wheel, as well as the type. So you can have the metallic wheels the ones as the NASA uses, or we can have the beach wheels, the balloon type wheels that is shown in the image, and those are the wheels that we are using currently in our rovers. These are 12-inch balloon wheels, which are low pressure beach wheels. And yeah, why are we using them? Why are we not using the metallic ones? So I'll come to that now. The ones that NASA uses are made up of titanium. Okay, so they are heavy, they are costly, and they have got great strength ratio, a great strength to weight ratio. But first, we don't have access to that much of titanium to get our wheels fabricated. Secondly, we don't have the suspension setup and the capabilities of the regards that NASA uses, so we need to make do with other setup. We earlier used to have the metallic wheels in our rover a couple of years back, but what happened after a bit of as the time passes, was like the wheels would tend to absorb the shock rather than let the suspension system do it. They would tend to absorb the shock, and that would impart dents on the wheels. So over the time, the wheel would turn to square, and we all know like wheels are wheels. Wheels are best when they are still round. So yeah. Now, what are the importance of the balloon wheels and what are the advantages? So first of all, like these use rubber, and the rim is made up of plastic. So yeah, these are lightweight. These save us a little bit on cost sides. Then what happens is when the rover is traversing through a rough terrain, and the shock that is imparted from the movement is not big enough, or like very little impulses, so the wheels itself can absorb the shock and give us an edge, and so that it reflects in the design of the suspension. So when we design the suspension which is based on balloon wheels, we do not try to impart too much of strength or weight to the suspension, because we know some part of the shock will be absorbed by the wheels themselves, and so we need less material and less strength for the suspension, and that saves us in both the weight and the money on the material. So instead of going for carbon fiber composites or maybe expensive metal alloys, we can just use normal stainless steel or even aluminum rods for best strength to weight ratio, and we can make do with it. So that's how the balloon wheels works, and these are usually filled up with low pressure, like filled with low pressure, not up to the brim in terms of pressure, because if you do that, the rover will tend to jump a little more, and that would bend the suspension setup or give some damage. So instead, we use these on the low pressure setup, where it not only uh, which not only checks the rover from bouncing but also gives us a little bit of extra shock absorption. Yeah. So that is more or less everything about the suspension setup. Now, if we think about why do we use these specific parameters and how do we decide which all to use, so that basically depends on our experience from past years, from what we see in the competitions when we go over there, what our competitors are using and how well it is benefiting them, and what are the advantages and disadvantages, what are the advantages and disadvantages of our own setup. Then we try to make changes accordingly, and bit by bit we come to the optimized setup. That again, then once we get to a setup which is optimized enough and we can't do any more changes to it, so then maybe just because we try to focus on the research part and make new things work, so we move up to a different suspension setup, which is which is nowhere close to the setup that we used to use earlier. So 2 3 years back, we had a bogie setup with metallic wheels and all, and now we are using a double wishbone setup, a modified one, with beach wheels. And the first time we used it was the last year. This year we are making improvements for the same, and we are also trying our hand on the rocker bogie mechanism. But yeah, since we are out of college, there is not much work done on it. So yeah, that's about chassis and suspension. Now Dhruv will take over for the next part.
Am I audible?
Yes.
Okay, so good evening, everyone. I am Dhruv Shah, and I am the electrical subsystem head of Team VYADH. Today, through my presentation, I'll be taking you through what components that are there in the electrical subsystem, and I'll explain that in brief. Next. Whenever we think of an electrical subsystem, it majorly consists of five components. One is the power supply, that is how do you want to supply power to your subsystem. Second is actuations, that is like how do you want to make that system move, like how do you want it to move forward, move backward, or something like that. Third is control, how do you want to control the actuators that you have put on your subsystem. Fourth are the sensors, so these are the sensors which tells you about your surrounding. And fifth is the communication. That is how do you communicate with your subsystem when it is far away from you. Next. This is power supply. So this is the LiPo battery over here. Why do we use this LiPo battery? The reason being that like it is a 14.8 volt battery, and the motors that we use in our rover, they basically require 14 volts to function. So as a reason we use the 14.8 LiPo battery. Then why can't we use any other batteries like nickel cadmium, or for instance any other nickel alloy alloy battery? The reason being that these LiPo batteries, they are very lightweight, and they have about four times the energy that the other nickel alloy batteries will have. Now, if you can look into the image, then over there you can see three things that are mentioned over there. One is the voltage, that is 14.8 volt. The second is 5000 mAh, that is how much current it produces per hour, that is 5 amperes per hour. And the next thing is 50C. What does this 50C imply? So 50C is nothing but just the capacity. So how can you calculate this capacity? So the battery provides 5 amperes per hour and it has 50C value. So once you multiply 50 into 5, that implies 250 amperes. So when you use your battery, it can run until 250 ampere of current is being utilized. It function properly until then. Okay. Next. Yeah. So second part is actuation. Actuation means like how you run your rover. So on our rover, all the actuators that we have used are rotary actuators, and they are the motors. And this time we tried to implement linear actuators in the robotic arm in order to get precise calculation. And like the most of the motors that we used in the rover are DC. So the next question comes, why this motor? So when you like the selection of the motor for the rover is like one of the toughest job. So how do you select like what motor you want to use for your rover? So for that you have to do certain torque calculation, and it is not that difficult. You have to look into few constraints like what is the total weight of your rover, how much angle does it, like what is the maximum angle of inclination, what is the radius of the wheels, etc. Once you do that, you get few value of torque, and you can find suitable motors which has or which provides that much amount of torque upon running. So that is why we use this motor. Then the next question is, why do we use motor drivers? So I don't know like how many of you have worked on motors and Arduino personally, but if you cannot directly provide the power to the motor, you need to have a component in between the motor so as to make the motor work properly and not to cause any damage. So the component that we use in between is the motor driver. What the motor driver does, it just amplifies the current so that your rover runs or your motor runs more properly. Then why can't we switch to stepper motors or servo motors? So like there are few advantages and disadvantages of the motors that we use. So the DC motors that we use are very efficient and they help us achieve maximum torque continuously for over a longer period of time. Whereas stepper motors, they are less efficient, and at high loads it tends to skip steps. Like it is running one step, one step, one step, but in some cases it skips two, three steps and goes on to the fourth. This can cause some problem while there is some motion. Next, so the next part comes is the control. So, we have so many sensors, motors, everything on the rover. How do we control them? So, our main controlling unit on the rover is Intel NUC. We just directly power this Intel NUC and it works properly. Then, for motors and other sensors, how do we control them? So, in order to control them, we use Arduino Mega. It is easier to code. It has ample number of connections available or ports available on itself, so we can like connect multiple sensors to one Mega, and it is not very costly. It is cheap. Next, so now the sensors. So on our rover, we have ample number of sensors. We use sensors in almost all the subsystems that we have. Like we use voltage level sensors, that is buck or boost converter, because like in our rover we have few components that require around 24 volts to function. So how do we supply that much power to that component? So in order to do that, we connect a boost converter. It takes 14 volts from the battery and it amplifies that voltage to 24 volts, and we supply that voltage to that component required. Then in the science setup, we have spectroscope and other sensors. And in the robotic arm, we use gyroscope or MPU6050 accelerometer so as to get the angles between the links. Then, along with this, we even use cameras on our rover. So the main reason for using cameras is that like they help us give live monitoring of the environment, and they give us live feedback, and we get to know that where our rover is headed or which direction it's going on. Next. Okay, so PCB. So what is PCB? So now I said many components that we use over here. So there are so many components on your rover. Now it becomes very difficult in terms of wiring these components and connecting them, and it is more difficult to find any flaw. Like if there is some problem in between, how do you get to know which component or which part is not working properly? So in order to you do that, we use PCBs. PCB is PCB stands for printed circuit boards. What it does is that whatever the circuit that you have, it tries to shrink it, and it is given to you in a form of a board. So like on the right side, you can see the PCB. That is the PCB that we used last year for our rover control, that is controlling the wheels and all that. Then from where can we learn PCB? So right now YouTube is like you get everything over there. There are like many softwares for PCBs available online. There are like few of the most commonly used are the Eagle and the Easy EDA. So what that does is that like if you search PCB designing Eagle, then you get a huge playlist teaching you all the functions of that software. And then if you have the circuit with you, you can design a PCB of your own. And it is very easy to manufacture, like print this, get this printed as well. And the softwares that we can use are Eagle and uh, Easy EDA, and there are even other softwares like Altium, SolidWorks, MATLAB, all this. Yeah. Next. Okay. So this is the pseudocode. So the pseudocode. So we did this code in Arduino, and when the logic of this code is that whenever you want to control your rover, you just press 8, 4, 6, or 2, and on pressing that the rover will start moving forward, backward, or any sideways depending on the function of the keys. And we input 0, then the rover stops, and it doesn't stop suddenly. It stops gradually, like so that there is not much load on the uh, so that there's not much load on the motors. And so how can we learn Arduino? So Arduino is like a very simple software, and even though if you don't have any knowledge, you can like learn it within 1 week. And after learning 1 week, you get to know what are few of the basic functions in Arduino, like the digital write or in mode, etc. And is it too tough to learn Arduino? No, like it is not that difficult to learn Arduino. It is easy, and if you have even minimum knowledge, or like if you are even a beginner, even you can write the code of a rover. It's not that difficult to do. Yeah, next. Okay, so that was pretty much from electrical, and now I'll hand over to Darshan to continue.
Yeah, am I audible?
Yes.
Okay, so hi guys, I'm Darshan, and I'll be talking to you about our GCS, which is the ground control station, and also I'll be talking to you briefly about our communication system. Next. So, what is the GCS? So, in our case, GCS is a web user interface which is basically built using HTML, CSS, JavaScript, and it's hosted using Node.js. We didn't go with anything like PHP because Node.js is very simple to use. That's the only reason. And this GCS, what is its purpose? So it has two main functions. One is to control the rover's action remotely from the ground station, and another function is to monitor the rover through visual feedback from cameras which are on the
That's the
rover,
only reason.
and to receive data from all the sensors and represent it in one location which is easily accessible from the ground station. Yeah, next. Yeah, this is an image of our rover from the camera, which can be viewed on the GCS. Next. So, what exactly does our GCS consist of? Like I mentioned before, it's a web user interface, and it has 5 pages. The first page, the launch page, or it's just like a home page, which allows you to navigate to other pages. And the next page is a camera page, from which you can see, you can get the visual feedback from all the rovers, from all the angles of the rover. And then is the controls page. From the controls page, you can basically control the movements of the rover and get all the sensor values. The other two I will explain as I go. Next. Yeah, this is how our launch page looks for this year. As you can see, it's just a simple design with HTML, CSS. So basically, we have 4 buttons in the middle which allow us to navigate to the other pages. So this doesn't have any functional value, but it's just there to look good. Next page. Yeah, this is probably our most important page, the controls page. So as you can see in the picture, we can basically control the movements of the rover itself and the robotic arm. So all the functions of the rover can be controlled from this page. And on the top left, if you can see the subsystem checklist. So this is a quality of life feature which we added this year, where you can check if each and every subsystem is ready before setting the rover in action. And if not, you can just make sure it is ready before setting it in action. Then below that, we have the controls for the robotic arm. And those 2 compasses are the magnetometers placed on the robotic arm and the rover, from where you can see the readings. And below that is the 4 arrow keys. So those are used to control the rover itself. So the direction and the movement of the rover, and the max straight PWM and the max turn PWM. So here we are just giving it a threshold value of sorts, which it should not cross, so that a rover can move within a normal speed, so that nothing gets damaged on the rover. Next. Yeah, this is our camera page. So basically, on this page, we can view all our cameras, and we have 6 cameras on our rover. We can view them. We can view multiple cameras at once or singular. We don't want to view all 6 cameras at once because of the bandwidth issue. If we view all 6 at once, the videos will be very laggy. So we tend to view only the most important ones, and we keep switching between them so that we don't hog up all the bandwidth. Next. Yeah, these are some more images which you can see from our rover. Yeah, next is the science page. On the science page, uh, we go to, okay, so for the competition that we go to, which is called the University Over Challenge, we have to check for signs of life and collect soil samples from our rover. So in order to make sure this happens, we have a science page on our rover from where you can get the readings from different sensors used specifically for the science tasks, such as the pH sensor, temperature sensor, spectrometer, etc. We can also, like to collect soil samples, we need to use a drill of sorts. So to collect the soil samples, the drill, which has to be controlled, is also controlled from the science page. And we also need to get visual feedback of soil samples for the science task. So which can also be viewed from here. Next. Yeah, finally we have the autonomous page. The autonomous page is used for another task we have for this competition, where a rover should move a certain distance to reach a final destination through certain waypoints. So on this page, obviously all this has to be done autonomously, as the name suggests. So on this GCS page, we can see our rover's current bearing and our target bearing, so that we know that our rover is moving in the right direction to reach the waypoints. We can also see the distance left, that is the distance, remaining distance in order to reach the waypoint. Next. Okay, so communications. On the picture on the left, this is our this is the antenna and access point we use on our base station, which is a sector antenna. We use a sector antenna because our rover will only be in a certain direction, and this provides an angle of 120 degrees. So because our rover won't be anywhere around us, only in front of us, so we can just use a sector antenna, which is cheaper and more effective than using an omnidirectional antenna. And this is on the base station. On the picture on the right is the omnidirectional antenna, which we use on the rover. On the rover, we need an omnidirectional antenna because the rover's yaw can be anything at any point based on how it moves. So it always has to be connected to the base station. So for this, we will need an omnidirectional antenna. Next. Okay, so for communication, ROS is very important. But why ROS? Okay, one of the most important reasons we use ROS is when we have to control the Arduinos on the rover, they have to be controlled using serial monitors. And ROS has this feature where you can control multiple serial monitors simultaneously. And ROS is also very simple to use. So based on these two factors, we selected ROS. And it's also like the tutorials are all available online. And it's very simple to learn and to use. So basically how our communication works is when we send a command from our GCS, a package which is where our ROS script is written. It publishes data to a ROS topic, and from our rover, another ROS script subscribes to this data and sends it on the serial monitor to the Arduinos. So with this, the Arduinos can be controlled. Conversely, when we want to get sensor readings from the rover, a package specifically built for this publishes data to another ROS topic, and again from the GCS end on the base station, we subscribe to this data and we publish it onto the GCS using our package called ROS-lib.js. which is a free of it's actually a free library available, and then these values are then displayed on the GCS as required. Next. Yeah, that's from the communication department.
Thank you, Darshi. So, if any one of you wants to ask question, they can raise their hands, and I think you guys can unmute yourself and ask the questions one by one. Yes, please go on.
There are few questions in the chat box. How to make it waterproof?
Okay, so Dhruv, can you please unmute, and I think you can answer this.
Yeah. So there are two ways to make the PCBs waterproof. One is that either you can apply some layer of coating on the PCB so that the water does not affect the circuitry and the components on the PCB. And the second way is that you can create an enclosure for the PCB. Enclosure over here means a kind of a box sort of thing in which you place your PCB. It is covered from all the four sides and it has some space left for your the wires to go out and the connections for that. Did I answer your question properly?
Okay, thank you.
Yeah, the next question was, can't we use graphene?
Yeah.
Sorry.
We use graphene for the rover's wheel.
Yeah, so basically, graphene is currently not available in the mass market, and secondly, the major applications of graphene so far are for the sensors and all applications. If we want to go use it for the manufacturing setups, we need to go for the sheets, and the graphene sheets that are available right now are being researched upon are not worth using for as a wheels. So this is from what I know about graphene and about like when you used to look for materials. So that's what we know. And secondly, like even if you were to even if the graphene was available for use, I think it will be too expensive for us to use, because if we use graphene wheels, I guess it will cost as much as a rover, the whole rover. So yeah, 2x the cost.
What are the digital modulation schemes that you use to transmit data?
Okay, so we use priority-based message transmission mechanisms, which is available in ROS for this.
Which event are you participating?
So that is URC and ERC, University Rover Challenge, and the European Rover Challenge. And we are soon planning to participate in IRC as well.
How much did it cost for your team to complete the rover?
Okay, so this is again a financial question, but basically our limit, which is set by URC, is we can't spend more than $14,000, and we somewhat sum up to be around the range of $7,000 to $8,000.
What are all the science experiments you conduct, as in what all you test for?
That will be taken up tomorrow. Tomorrow we have the robotic-arm system, the science system, as well as the management aspects of the rover. So this question will be answered tomorrow.
What wavelength do you use to communicate with the rover? What is the reason for the choice?
So we use 2.4 gigahertz frequency to communicate. This is mainly because 5 gigahertz gives us good good speed, but then it does not have enough range. Our base station has to be around, say, 1 kilometer away from our rover. Sorry, our rover has to be 1 kilometer away from our base station, and 5 gigahertz does not give enough range for this to happen. And another reason is, say, 900 megahertz is very less. It does not give enough speed to, say, get good quality of video. It'll always be laggy most of the time. So in order to achieve the middle ground, that is get good range and good quality, we use 2.4 gigahertz frequency.
What steering mechanism do you use? How did you choose it?
Okay, by steering mechanism, I think you're trying to ask how we move our rover left, right. So actually, that is just simple code manipulation. Actually, not code manipulation, it's just simple coding where with suppose when we are controlling it through our laptops, if we press 6, the rover goes right. If we press 4, the rover goes left. And 8 is forward, 2 is backwards. It's just the, I mean, Dhruv did mention that we code it on Arduino, and over there we give in certain commands that with certain inputs from the keyboard, PWMs of different motors change. So we have 4 motors here, 4 motors on a rover, and that is how we command them to move. This is because there is actual no steering. We are never close to our rover. Our rover is somewhere out in the field, and we are sitting in a room. So the only steering mechanism that we do have is the code that we've put on our rover wheels, and with the inputs that we give, it moves. I hope that is what you asked for.
What are the onboard systems do you use and how did you integrate it with the web page?
Okay, so onboard systems basically is the electrical system, the communication system, the science equipment, the robotic arm, and the wheels, and the cameras. So basically, on ROS we will know whether we are receiving data or not from a certain package. So when we are receiving data, we will say that system is running. So that's how the system's checklist works. So using ROS and a library called ROS-lib.js, which is a JavaScript library, we will be able to integrate this on our webpage.
Can you tell the material that you are referring for this kind of suspension system?
Yeah, so this is basically aluminium for the uh, for the suspension system, like the aluminium rods, and some of the parts are made up of stainless steel.
The material in the sense, book.
Oh, okay. No, like it's just like what we basically like. We work on an approach that we learn the stuff from our seniors who have worked on the rover for a year or two. Then they teach us the process through the whole year, and then we consult like the research papers that are published on the same. So if you go to Google Scholar and search for rover traversal mechanisms, like you will find a lot of suspension systems and all. So we take help from there. If you want some specific help, regarding the very basics, maybe you can refer some book on vehicle dynamics. that would help. But as I said, like most of the setup is different from the normal automobile suspension systems. We need to just go on to the experience that we have got from previous years. So as of now, like we are teaching our juniors on what to do and what all they can do, what we failed to do, and stuff like that. So it works that way. I think we missed one question earlier from Shrijit. So yeah, the steering mechanism, actually we don't need a steering mechanism at rover. What we do is basically we work with the wheel spin, that RPM of the motor. So if you want to turn right, for example, we'll decrease the RPM in the command, the code that we use in the Arduino. So it will decrease the RPM of the motors on the right side, and it will increase the RPM on the motors on the right side. So what it will do is it will move in a slow arc. So it will be a big move, but it will eventually turn the rover around, because this keeps the steering mechanism simple and easier to use, plus saves us a lot of weight, and we don't actually need a lot of steering movement in the rover. Yeah, Ackerman. Yeah, it depends on the terrain that we are currently on. So like in case we are on a smooth terrain where we don't have any issues of the rover strucking up the wheels, getting stuck in sand or anything, we'll go for Ackerman. But if you want to have a big arc around a bigger obstacle, we can go for the low and high RPMs.
Hi, am I audible? Hello?
Yes, yes.
For the GCS, you had mentioned the camera feeds, right? So does it go through a central server mechanism, or like it's direct, like one-on-one to your rover and your ground station?
Okay. This actually there is a central server mechanism. So using ROS, we have 6 packages, one for each camera feed, that is. And these, using ROS, all the 6 packages are accessed simultaneously and can be turned on and off whenever necessary. So yeah, we are using a central server.
Is the server through the internet, or it's like your private server or what?
I'm sorry, I couldn't hear you.
Is the server through the internet, or it's your private server? Or
No, it's just a private network. It's not through the internet. There's no internet access available there.
For the autonomous system, do you use LiDAR or is it directly through camera feedback?
For this, we use stereo cameras. For the time being, we use stereo cameras.
If we have no questions, we can end today's session.
Yeah, I'll just add on to that. You can use lidars. I think at the end it just depends all on the. There are a lot of other constraints that comes while designing a rover. I mean, if you have enough money, I could say you could really build a top-notch rover. But the thing is, there are always constraints such as finances, how you handle, how much money you can raise. So sometimes there are always better alternatives to what we have on a rover, but it's just that every good idea always cannot be implemented. There are always constraints either from one of the departments, or there are money constraints, or you can't blow up your entire budget. So there are a lot of aspects. And to one question, who was like the material, I would say the best way to go about making a rover team is to just build something and test it. Building something and testing is the most assured way of learning than going through 40, 50 research papers and putting all your work hours over there. Maybe refer 2, 3 papers, try and build something out of it. If it works, good. If it doesn't work, well, you know what not to do. That is how we have learned. That is how our seniors learned. That is what we are telling our juniors who will lead the team next year. So more than focusing just on the theory aspects of it, maybe getting your hands dirty, building something, blowing up stuff, which happens a lot actually, is the most assured way of learning.
If we have no questions, we can end today's session. Okay, what are the main parts of Lunar Rover?
Yeah, so basically about the Luna rover, so basically from what we know about the NASA missions and all, they don't have a lunar rover to be exact. They use moon buggies. So those are basically not non-autonomous systems that humans drive. So they have seats and all the basic requirements of a normal car and all. But if you talk about the rover, for example, the Vikram lander that ISRO used in the mission, it was basically very same as that of the Martian rovers, the same rocket bogie suspension setup and a robotic arm attached on the top, completed with a power system and communications uh, for the communications to the satellite orbiting around the moon, and then via that link to the ground control.
Yep. Also, you had mentioned autonomous control through camera feed, right? So, is there any object detection algorithm that you have used, or
Yeah, so basically, we work on the codes ourselves, and we use a Kinect to detect the objects in the vicinity of the rover, and then through the same procedure, we try to find a more suitable route in which the rover should take, and then it feeds the same to the electrical subsystem, which powers the motor code in the same way, so that it travels in the specific direction.
What else do we need to study?
Yeah, so
Okay, Arun, you answer.
yeah, so it just depends on first of all, like you need to consider what all parts you have to uh, what all parts you need to include in a rover. So basically, it depends on the competition that you are trying to participate in, and that all the competition have certain rules and regulations that you need to follow, and certain tasks that you need to do. So for that, you need to make necessary changes, and for those changes, you need to study about each part differently, because none of the parts that we use in our rovers is similar to any other normally used widely used parts. For example, in our system, when we talk about robotic arm tomorrow, we'll tell you about how we use grippers and end effectors for the robotic arm. So those are used in everyday robotics, but not all in a not all in a same machine. So we use design ideas from different machineries or different industries at all, and then get a mixture of those to work to get work with our tasks and all. So it just need to it depends on what all you want to what in your rover, and how much you are willing to make changes to the specific part. If you want very specific to your ideas, then you don't have to actually read anything. You just have to consider in detail what you want your machinery to do, and then you want to make changes accordingly.
Hello guys, I'm Aditya. I suppose there are some questions on autonomous. What kind of object detection that we use? We basically take a molecular image, take out the depth of it, and then we use segmentation. So basically, it's SSOD. So you use semantic segmentation of the images to take out the object detection from that neural network. It's a very simple R neural network, RCNN, from which you get the object detection. Basically, you take out the depth of the image, you make a point cloud of that, and as soon as you get the point cloud, you are sure that you have to avoid that area. So, because our rover is off terrain and not the autonomous car that will be running on the road, so the kind of objects that we have to detect are much more different. You can simply take out the point cloud of the environment and simultaneously move across it.
So for detecting the depth, what do you use? Is it IR or parallax method?
Basically, what we are using is there are two methods. One is the new method where we are using a molecular image and we are taking out a neural network. We have made a new neural network. You take out the depth of the image directly from the molecular image. And the second part that we will be fusing it is directly with our Kinet V2 sensor. Kinet V2 is a stereo camera that gives you directly the depth. So it's plain and simple. You take the stereo camera, apply it. As soon as you run it on your ROS framework, you will get the simulation. On running the ROS launch, you will get the depth.
Can you send any links for study rovers?
Rover has many types of mechanism. So what kind of field you are willing to work, you have to learn in a different kind of subparts. For example, our team has 5, 6 subparts where we are working on autonomous mechanical uh, robotic hands. So there are many courses for the same. We will be giving you the links. Do you guys have any further question related to autonomous traversal?
If we have no questions, we can end the meet.
Regarding the links, tomorrow we will be sending you some of the links for the autonomous traversal.
All right.
I, on behalf of SEDS KCT, the entire crew behind the event and myself, want to extend a hearty vote of thanks to the VYADH team of VIT SEDS and also all the audience who graced the event in great numbers. Thank you VYADH team for providing an informative talk and also for sharing your experience in building a rover. Thank you for spending this great evening with us and have a great day. Day 2 of this webinar will continue tomorrow again at 5 pm. Thank you all.
Sir, please send the feedback form.
Come again?